Dear students, in this session, we'll learn about alkynes. Alkynes. Alkynes, in earlier session, we discussed about alkenes and alkenes. These alkynes are unsaturated hydrocarbons. Alkynes are unsaturated hydrocarbons. Already in unsaturated hydrocarbon, we studied carbon-carbon double bonded compounds. Carbon-carbon double bonded compound is nothing but means carbon-carbon single bond paraffins, carbon-carbon double bond olefins. Okay, carbon-carbon single bond paraffins, little affinity, little reactive. Carbon-carbon double bond paraffins, oil forming. Okay, similarly the triple bonded compounds are called carbon-carbon triple bonded or alkynes. Carbon-carbon triple bonded or alkynes. Alkyne, A-L-K, alk is a root word, Y-N-E, wine is a suffix. So carbon-carbon triple bond to the root word, that is alkynes. These alkynes will be having the general formula. What will be the general formula? And how it will be exist, everything will be the structure of an alkynes, chemical reactivity, physical properties and chemical properties will be discussed in this session. Okay, so alkynes are carbon carbon triple bonded compounds. Alkynes are unsaturated hydrocarbons having carbon carbon triple bond, and alkynes form homologous series. Alkyne forms homologous series. Homologous series means differ by CH2 group is called an homologous series. Differ by CH2 and this carbon and hydrogen, that is 12 plus 2, that is equal to 14 units. 12 plus 2, that is 14 units. Differ by the 14 units, that is homologous series, means differ by CH2 group is called homologous series. General formula of alkynes is CnH2n minus 2. CnH2n minus 2 is a general formula. Minus 2 because forms a triple bond with the removal of hydrogen. The first member of alkyne series is ethine or acetylene. The series we call as ethylene or acetylene. Acetylene mixed with an oxygen used on welding purpose. Like alkene and alkyne, it also exhibit isomerism, especially structural isomerism. And the carbon-carbon triple bond contains 2 pi bonds and 1 sigma bond. The basic bond, what it forms is sigma, then the other 2 bonds are the pi bonds. Okay. In alkyne is an unsaturated hydrocarbon having a carbon-carbon triple bond. Homologous series, which also forms in homologous series. Homologous series, you can say carbon-carbon triple bonded compound. Means C1, you can chuck this C1H2 into 1, 2 minus 2, C1H0. Compound doesn't exist. So C2H2 to the 4, 4 minus 2 is 2, C2H2, hydrogen and hydrogen. The first compound in this alkyne series is eth and by any eth and ethine also recorded as an acetylene. Ethine, the series is also recorded as acetylene series. So carbon number 3, C2H2 is C1, no? Means second carbon, C2H2. Carbon number 3, C3, 6 minus 2 is 4, C3H4. C3H4. Okay, so in the case of the carbon, 2, 3 is 6, 6 minus 2 is 4, C3H4. Next is C4H8. C4H8 minus 2 is 6, C4H6 and C4H8 and so on. So what it is, difference between ethane to propyne is 1 carbon and 2 hydrogen. 1 carbon and 2 hydrogen, that is CH2, differ in CH2. So CH2 12 plus 12 carbon plus 2 hydrogen, that is equal to 14 unit. This is called homologous series. Homologous series. Okay, so alkynes, carbon carbon triple bond, and general formula CnH2n minus 2, and there will be homologous series CH2, C1H2 or CH2 differ by 14 units. And acetylene mixed with an oxygen, it will be used in the welding purpose. Oxy welding, acetylene carbon carbon triple bond used, and oxygen will be using for welding purpose. As like alkene and alkene, alkyne also shows isomerism, especially structural isomerism. And carbon carbon triple bond, out of this carbon carbon triple bond will be having one sigma bond and two pi bond. One sigma bond and two pi bond. This is about alkenes. Next, we need to study about the structure. Structure of alkynes, carbon carbon triple bond. Carbon carbon triple bond, in this, what you are noticing here is a carbon, and the second one, the right side, is a carbon. One carbon, and here is in one carbon. In that, it undergoes sp hybridization. One s orbital combined with one p orbital undergoes an sp hybridization. Sp hybridization means we'll be getting two hybrid orbitals. This is one hybrid orbital. Again, this is another hybrid orbital. Similarly, for this carbon, we'll be having one hybrid orbital. Another carbon, this carbon will be having, same carbon will be having hybrid orbital. Out of the three p orbitals, one p orbital combined with s orbital undergoes an sp hybridization. These 2 and 3 are unhybrid orbital in this carbon, carbon number 1. And second carbon, this will be 2 and 3 unhybridized orbital. These two will be overlap with each other, will be forming this above and below one pi bond, and this will be forming another pi bond, totally which forms and two pi bonds. Similarly, and this orbital, this NSP, p orbital, no, here, this one s orbital will combines with p orbital. This will binds with hydrogen, will be forming the linear structure. Linear structure, that is 180 degree. Linear structure, that is 180 degree. So two carbon between the two hydrogen, between them is triple bond, that is acetylene. That is acetylene means triple bonded compounds, means triple bonded compounds. So how this will be having hybridization? What will be the bond length? Okay, so what I explained, you can notice here. Alkynes carbon atom joined by triple bond is an sp hybridization. Sp hybridized. Sp carbon atoms are linked to one another by the two pi bonds and one sigma bond. These two are pi bonds. This is pi bond and this is sigma bond. This is both are same. Don't consider as four. Two pi bonds and one sigma bond. And in this carbon carbon triple bond is the shortest out of carbon carbon single bond, carbon carbon double bond, and carbon carbon triple bond. Carbon carbon triple bond, that is 120 picometer. Carbon carbon double bond, it is 132 or 134 picometer, and carbon carbon single bond 154 picometer. You can notice that bond order increases, the bond length decreases. Bond order and bond length are inversely proportional. And in this, above and below, the electron cloud density. Electron cloud density means laterally they'll be overlapping with the two pi bond. It's completely forbidden the restriction of the carbon carbon bond. Means the carbon carbon here in sigma bond, this complete electron density is above and below. It avoids the free rotation, so we cannot get rotamers. We cannot get rotational isomers in alkynes as like alkenes. And the electron cloud between two carbon atom is cylindrically symmetrical above and below. Okay, above and below, it is cylindrically symmetrical. And this is about internuclear axis, led to the main axis. If you consider, no, this is an internuclear axis. If you consider there's an internuclear axis, so that is uniformly distributed. And ethylene or ethine is a linear molecule. Hydrogen, carbon, hydrogen. So the bond angle is 180 degree. That's 1800, not that is not 1800, that's 180 degree. And sp carbon atom are more electronegative than sp2 and sp3. It is roughly and 50. One s orbital and one p orbital, that is 50% s character. Okay, this is the structure of acetylene or structure of alkynes. In alkynes, there will be triple bond. There will be triple bond, sp hybridization, bond angle 180 degree, linear structure. Carbon carbon triple bond length is 120 picometer compared to carbon carbon single and double. This is the shortest. Okay, shortest bond length. So this is the structure of the carbon carbon triple bond, especially acetylene. Okay, next about the nomenclature. Isomerism, we know isomers having same molecular formula and the same structural formula, but differ in the chain, differ in the norm, especially in the chain isomers, chain and position isomers will be noticing in alkynes. In that the chain isomers, so the chain will be straight chain or branched chain. 1, 2, 3, 4 butane. Okay, in the first carbon will be having triple bond butane. Okay, one butane, 1, 2, 3, 4. Out of the third carbon will be having the methyl group. So name of IUPAC, name of the compound is 3-methyl but 1-ine, YNE, 1-ine or 1-butane, both are same. Similarly, the same means total 3 plus 2, total 1, 2, 3, 4, 5. So this can be right as linear also, means will be 1, 2, 3, 4 will be having a triple bond. So 1, 2, 3, 4, 5 is nothing but pent, carbon number 5, pent. And the first carbon will be having 1 YNE, one pentine. One pentine means having the same molecular formula and the differ in their structure are called structural isomers, especially the chain will be differ in the structure, especially chain, straight chain and branched chain is an example for chain isomer. Similarly, the position isomers means the position of double bond, where it will be, means this will be having a carbon atom 1, 2, 3, 4, 5. That is one first carbon will be having carbon carbon triple bond. So pent 1-ine, pent 1-ine or 1-pentine, both are same. In this carbon carbon double bond is changes to first carbon to a second carbon. If it changes to first carbon to second carbon, then the numbering will be differ. Means position of isomers will be differ. Position of triple bond is differ. So first carbon to a second carbon, then it will be 2-pent-ine or pent 2-YNE. So chain isomer and positional isomers. Chain isomers and positional isomers in alkyne. Next, how the alkynes are prepared. How alkynes are prepared from the calcium carbide preparation of, means we can prepare alkyne from carbides, especially calcium carbide. On industrial scale, ethine is prepared. We'll be studying about ethine, that is especially carbon carbon triple bonded, two carbon with a triple bonded is called an ethine. And in ethine large scale, in industrial scale or large scale, ethine is prepared by treating of calcium carbide with water. And calcium carbide is prepared by heating quicklime CaO with coke, CaO, calcium oxide. So how it will be prepared? So I'll write the equation. So calcium CaCO3, calcium carbonate. So calcium carbonate decomposed to form calcium oxide and carbon dioxide. This calcium oxide CaO treat with the carbon carbide. So C carbide, which gives CaC2. What it is? S, which gives CaC2, calcium carbide with formation of carbon monoxide. So this calcium carbide CaC2 is treat with water. CaC2 treat with water. 2H2O will be gives carbon-carbon triple bond CH and CH with the formation of CaOH twice calcium hydroxide. This is the industrial method of the preparation of alkene, especially that's ethene carbon-carbon triple bonded compound. So this can be obtained by heating of limestone. Calcium carbide will be getting by like limestone. Limestone is calcium carbonate, no, CaCO3. So this is also recorded as preparation of alkyne from carbide, calcium carbide. So we can see the equation CaC2, calcium carbide, treat with water will be forming calcium, means carbon-carbon triple bonded compounds of alkyne with the formation of calcium hydroxide. So carbon-carbon triple bond, where we are getting calcium carbide? So heating the limestone, calcium carbonate, heating of limestone give rise to calcium oxide and carbon dioxide. This calcium oxide treat with carbon will be forming calcium carbide. This calcium carbide treat with water will be forming calcium hydroxide along with carbon-carbon triple bonded compound. So preparation of alkynes from carbide, calcium carbide. Okay. Next is from vicinal halide. From vicinal halide. We know that vicinal halide. So halogen group attaches to the neighboring carbon adjacent with each other, then it is called vicinal. So vicinal dihalides. Vicinal dihalide, first we know the preparation. Vicinal dihalide treat with alcoholic potassium hydroxide. Earlier we studied alcoholic KOH, potassium hydroxide, undergoes dehydrohalogenation, removal of halogen as well as hydrogen. One molecule of hydrogen halide get eliminated. One molecule of hydrogen halide get eliminated, forms alkynyl. Alkynyl, okay, and which on treat with sodamide, NH2 is called sodaamide, which is triple bonded compound. So what it will be? Vicinal dihalide is nothing but carbon, double bonded carbon, sorry, adjacent carbon will be having halogen, this X. So rest will be H, this will be hydrogen, and there will be substituent group R. This will be treated with alcoholic KOH, potassium hydroxide. So hydrogen and halide needs to get eliminated. Dehydrohalogenation. Dehydrohalogenation. With the removal of HX will be forming RCH, double bond. With the removal of halogen, what it will be? If halogen and hydrogen get eliminated, then CH double bond, this CX halogen and H will be forming. So this is we call as alkynyl. This alkynyl halide treat with sodaamide. This will be treat with NaNH2, sodaamide. Then hydrogen and halogen get eliminated, will be forming carbon-carbon triple bond. Carbon-carbon triple bond. Alkynyl halide to alkyne or alkyne or C, triple bond C with H. This group will be forming. So this is called as vicinal dihalide. Vicinal dihalide treat with alcoholic potassium hydroxide. Then what happened? Hydrogen and halogen get eliminated. So not this one. Hydrogen and halogen get eliminated. Then what happens? Then dehydrohalogenation. Means R group and hydrogen. One hydrogen and one halogen get eliminated. So then what will be getting? So alkynes, sodamide, NaNH2. NaNH2 is called sodamide. Amide is NH2. Na is sodium, sodamide. Okay, we'll see the chemical equation. So vicinal dihalide treat with alcoholic potassium hydroxide. Then what happens? So undergoes dehydrohalogenation. So halogenation, hydrogen and halogen, H combines with X will be forming HX, removal of H, this X, and halogen will be combined, hydrogen, HX will be removed, will be forming alkynyl halide, treat with sodaamide, will be forming alkyne. Okay, so carbon-carbon triple bonded compound. And we can see the few more examples. This one, CH2, BrCH2 means carbon 1, 2, that's ethyl. So ethene, that's 1 comma 2, 1 comma 2 bromo, 1 comma 2 dibromoethene. It will be treated with alcoholic potassium hydroxide, alcoholic potassium hydroxide, KOH. So this is 1, 2, 1 comma 2 dibromoethane, which will be treated with alcoholic potassium hydroxide. So what happened? So hydrogen combines with bromide, get eliminated HBr, HBr and water molecule. Then what will happen? Will be forming carbon-carbon double bonded, means with the removal of this bromine minus KBr, one bromide will be left behind. So we'll be forming double bonded compound. So this CH2, CH, and this will be Br. One electron which will be formed double bond, carbon-carbon double bonded compound. This is what we are getting. Okay, this alkynyl bromide, treat with soda amide NaNH2, NaNH2. So if we treat with NaNH2, what happened? So sodium combines with this bromide, will be forming sodium bromide, and hydrogen combines with this nitrogen, will be forming the NH3 ammonia, N and H3. So what will be left behind? One electron, one hydrogen free from this NH. I'll write here. So carbon double bonded. Here hydrogen and hydrogen, and here hydrogen and bromide. Bromide combines with this one, sodium. It forms an NaBr. Then hydrogen combines with nitrogens to form ammonia, NH3. So the left behind thing is, if it is here, not there, here, not there. One electron and one electron, they binds together, will be forming triple bond. Okay. Similarly, this is vicinal dihalide. As like vicinal dihalide, in geminal dihalide also opposite. Means if the halogen group attaches to the same carbon, if R, C, and this will be hydrogen, CH2, and this carbon, one halogen and another halogen. Sorry, not hydrogen, that is halogen. So if halogen attaches to this is hydrogen and this is hydrogen. Now it is gem dihalide. Gem dihalide. Treat with the same of alcoholic potassium hydroxide, KOH. So what happened? Hydrogen halogen get eliminated as HX, will be forming the free double bond. So between them it forms a double bond, carbon-carbon double bond here. So carbon-carbon double bond, and will be having one hydrogen and R group. Hydrogen here, halogen, one halogen get eliminated, left behind with this one halogen and hydrogen. This treat with soda amide, NaNH2. If we treat with this with soda amide, then we'll be getting this halogen get eliminated, along with this one hydrogen get eliminated, this electron and this electron forms a triple bond. We'll be getting carbon-carbon triple bond, alkyne, alkynyl halide to alkyne. So that is gem dihalide. Gem dihalide. This is an example for gem dihalide. This is an example for the vicinal dihalide. Vicinal dihalide adjacent halogen groups. You can notice no bromine. Both the bromine will be present in same side. And the halogen, example here bromine and here bromine, they'll be present in, means attaches to same carbon. Then it is called gem dihalide. Gem dihalide and vicinal dihalide. Treat with alcoholic potassium hydroxide, which forms alkynyl halide, which treat with soda amide, gives alkyne in both gem dihalide as well as vicinal dihalide. Okay, these are the important methods of preparation. Important methods of preparation. Which are the important methods of preparation? Industrial scale. A large scale of the alkynes are prepared from calcium carbide, CaC2. Okay, next is from vicinal dihalide and gem dihalide, other two methods. Next, after this, physical properties of alkyne. Alkynes are colorless, odorless, tasteless compound. Lower alkenes are partially soluble in water. Lower alkynes are partially, not completely, partially soluble because of steric hindrance between them. Higher alkynes are insoluble in water. And the completely soluble in organic solvents. These will be non-polarity means usually they'll be soluble in organic solvents. No, they'll be soluble in organic solvents. Melting point and boiling points are directly proportional to molar mass and inversely proportional to number of branches. Molar mass increases, the melting point also increases. Then the number of branching increases, the melting point and boiling point decreases. Melting point and boiling point are inversely proportional to branching. Branching. So molar mass is directly proportional to melting point and boiling point. Up to carbon number 4, alkynes are gaseous. C5 to C11 are liquids and C12 above are solids. Okay, C4 till to carbon number 4 alkynes are gaseous. C5 to 11 are liquids and C12 above are solids. These are the physical properties of alkynes. Next, after that, we'll see chemical property. In chemical properties of alkyne show acidic nature in addition reaction as well as polymerization reaction. Why this show reaction? Because we'll be having triple bond. Triple bond means higher the bond order, repulsive force is more, reactivity is also more. So acidic nature of alkynes, we need to get monoacidic, monosubstituted. So how it will be mono or with a using of sodium metal or soda amide, how this strong bases can react with ethyne, we need to be studied. So in that carbon-carbon double, single, double and triple bonded, how the order of reactivity, ethyne, ethene, ethene, and we need to study. As well as it shows an addition reaction. Acidic reaction. Next, addition reaction, because here we'll be having a triple bond. No, due to the presence of triple bond, it shows an addition reaction. Addition reaction we studied in earlier, with hydrogenation, addition of hydrogen in presence of platinum or palladium or nickel catalyst. If we used the palladium in activated charcoal is called Lindlar catalyst. That is also known as Birch reduction. You need to remember Birch reduction is the same as Lindlar catalyst. Lindlar catalyst. If you use a Lindlar catalyst, yeah, palladium in activated charcoal, that is called Lindlar catalyst. Okay. Now, chemical properties. First one, I said acidic character. Next, we need to study addition reaction. Next, after that, addition of dihydrogen H2 means in addition reaction dihydrogen. Similarly, addition of halogen, addition of dihydrogen, addition of halogen, addition of hydrogen and halide, addition of water H2O. Next, polymerization. These are the chemical properties we need to discuss. We'll discuss one by one. Okay, first one, addition, acidic character of alkyne. Sodium metal and sodamide. Sodium metal Na and NaNH2 sodamide are the strong bases. And they react with ethyne, triple bonded compound, to form sodium acetylide. Sodium acetylide means double bonded, triple bonded compound treat with sodium will be forming triple bonded with Na group adds to this, sodium group adds to carbon triple bonded compound. That is what we call as ethynide compound. If single sodium, monosodium ethanide. If the two sodium adds to that group, disodium ethanide, or etc. Okay, so in this strong basis of sodium and soda amide bases, they react with ethyne to form sodium acetylide, which the liberation of dihydrogen gas H2 will be liberated. In the case of two carbon, in the case of the third carbon number 3 onwards, hydrogen combines with nitrogen will be liberated as NH3. NH3 gas will be liberated in propane. Okay. Next, in this reaction indicates ethane is acidic nature. This is because in ethane, hydrogen atoms are attached to sp, 50% s character, 50% s character, more electronegativity than sp2 and sp3. So s character in sp3 and sp2 is less compared to sp. So more of its character, more the acidic nature. This is what we discussed in first chapter. More of the S character, more is the acidic nature. Okay, so triple bonded compound treat with triple bonded alkyne, means carbon carbon triple bonded compound treat with sodium in presence of soda amide. So this sodium will attaches to this carbon NH, hydrogen and hydrogen. So what happened? Sodium get attaches to this, will be forming carbon carbon triple bond with sodium, and one is hydrogen. Then half of hydrogen gas, means H2, half H will be liberated. Hydrogen get liberated. This is only one sodium, no, that is monosodium ethanide. Monosodium ethanide. Similarly, carbon carbon double bonded triple bonded compounds, this one treat with the sodium, this product. So mono sodium ethanide treat with, this is Na, treat with again sodium metal. This another hydrogen get replaced by the sodium, will be forming NaC triple bond C Na. This is Na plus and C minus, Na plus and C minus. With the liberation of half H2 and half H2, that is complete 2H2. H2 will be liberated. So that will be disodium ethanide. Disodium ethanide. Okay, this is how the acidic character, means reaction, it shows carbon carbon triple bond shows an acidic nature. And in the case of triple bond, so in the case of triple bond in 3 carbon, so in the case of triple bond only, that's 3 carbon. In the case of 3 carbon, this sodium NaH2, so CH3, C triple bond CH. Okay, this will be treated with 1, 2, 3 propine treated with sodium metal. So Na plus, so NaNH2. In that sodium get replaced by one of the hydrogen. Okay, this hydrogen NH2 and H will be formed as NH3, will be forming CH3 C triple bond C Na plus NH3. So sodium propanide, it forms sodium propionide, PROPYNID, sodium propanide with the formation of ammonia. This reaction can be used to distinguish alkynes from alkenes and alkenes. From alkenes and alkenes, we can this process. These are the reaction. With the using of this reaction, we can able to identify the reactions. So alkyne means triple bonded compound. The acidic character means triple bond is more acidic character than double bond and single bond. So in the case of ethyne, ethene and ethane, ethyne, ethene and ethene. So it's ethyne is greater acidic than ethene, carbon-carbon double bond, than carbon-carbon single bond. Among alkynes, the terminal alkynes are more acidic. Therefore, the acidic order of the character of ethyne, propyne, and butane. If you consider ethyne, propyne, butane, so ethyne, carbon-carbon double bond, the terminal hydrogen is more acidic. This will be greater than propyne. This 3 carbon, it will be greater than the carbon number 4. It will be greater than carbon number 5, and so on. So acidic nature, you need to remember the acidic nature. So how is a chemical reaction? I'll show the chemical equation. So triple bonded compound ethene are treated with sodium, will be forming. Sodium is replaced with hydrogen, any one of the hydrogen, that two terminal hydrogen. Any one hydrogen is the last hydrogen, terminal hydrogen. So it will be formed Na plus and NH3. This sodium will be binds to this sodium, only sodium metal. So with carbon number 3 onwards, why we are writing only sodium here? After that, NaH2. So sodium is enough to replace here. In the more of carbon number 3, carbon number 4, 5, 6 and all, will be using soda amide, the mixture of sodium and ammonia, Na and NH3, NH2, soda amide. So hydrogen, this will be replaced by this hydrogen. Hydrogen get eliminated, will be forming the HC triple bond, this with Na. Then single sodium, monosodium ethynide with half of H2 hydrogen. No? Then monosodium ethynide is treated with this product is treated with again sodium, will be getting disodium ethynide. Okay, next in the propyne compound, carbon number 3. In carbon number 3, so 1, 2, 3. So treat with sodium soda amide, will be getting sodium propanide and NH. This reaction used to distinguish between alkene and alkyne. So alkynes are more preferential acidic character than alkenes and alkanes. Why? Because this S character is more greater compared to double bonded and compared to single bonded. In single bond and the S character is less, slight increases more than 50% here. Okay. So they're 33% and 62%, 63% and 70, almost 50%. So here, what will be happening? So among alkynes, terminal alkynes are more acidic. Terminal alkynes are more acidic in alkynes. Therefore, the acidic character of ethyne is greater than propyne and butane. Propyne and butane. So in the propyne and butane, so the order C double bond C is greater than 3 carbon, greater than 4 carbon, extremely greater than 4 carbon. Okay, so this is acidic character in alkyne. So let's see addition reactions. In addition reactions, we know that alkane contains triple bond, so they can easily add. We can add hydrogen, halogen, both hydrogen and halogen, etc. But addition of unsymmetrical alkenes must be follows Marconi-Curves addition. According to Marconi-Curves addition, majority of the reaction of alkynes are example for electrophilic addition reaction. Marconi-Curves addition, negative part of the adding molecule adds to the carbon containing least number of hydrogen is called Marconi-Curves addition. In unsymmetrical alkene, well follows Marconi-Curves rule. You need to remember. Okay, so we'll see an example one by one. So first one, addition of dihydrogen. This is addition of dihydrogen H2. So carbon-carbon triple bonded, when we use platinum, palladium or nickel catalyst, one hydrogen adds to this carbon. Carbon-carbon triple bond. So electron density, here more, hydrogen get adds up. Then 1 mole of hydrogen, then it becomes carbon-carbon triple bond become double bond. Then CH2 and CH2. For again this treat with dihydrogen, 1 more hydrogen adds to this double bond become carbon-carbon single bond. So this is platinum, palladium with the use of catalyst. Okay. Similarly, in a propyne is treated with platinum catalyst in presence of any one of this catalyst and hydrogen will be getting propene. Again, treated with hydrogen will be getting propane. Next, addition of halogen, especially bromination. When the propyne is passed into a bromine solution in CCl4, carbon tetrachloride. Okay, bromine solution, carbon triple bonded. Okay, in this will be treated with bromine, Br and Br2. So what will happen? One bromine attached to this carbon and another bromine attached to this carbon will be getting 1,2-dibromopropane. 1,2-dibromopropane, that is 1, 1, 2, means again this will be, it will be formed 1,2-dibromopropane. So one bromine attaches here, one bromine attaches here. Again this will be treated with bromine Br2. Again an adjacent side, opposite side hydrogen again replace it by bromine, will be getting 1, 1, 2, 2, tetrabromoPropane. Will be getting tetrabromoPropane. This is halogenation reaction. So we'll see chemical equation. So this is treat with alkynes and treat with bromine. So this is Br2. So treat with the bromine here. One bromine attaches here, another bromine attaches to here. Then double bond becomes triple bond become double bond. So this is one side, carbon attaches to bromine, another side with hydrogen. Okay, similarly, here again another hydrogen treat with a bromine, another hydrogen is replaced by bromine, and here also another hydrogen replaced by bromine. We'll be getting 1 comma 1, 2 comma 2 tetrabromopropane. Tetrabromopropane. This is the addition of halogen. Similarly, one halogen together is called hydrohalogenation. Is called hydrohalogenation. Is also called as hydrogen halide. Hydrohalogenation is also called as hydrogen halide. Two molecules of hydrogen halide, HCl or HBr, HRI, added to all kind to form gem dihalide, in which two halogens are attached to same carbon. If we used hydrogen halide will be getting gem dihalide. So in this alkyne, what you're noticing, what you are looking on the screen, carbon triple bond. When we add HBr, addition of the carbon, for the symmetrical, no problem with the symmetrical, no. Only unsymmetrical is a problem. For the symmetrical, no problem. Here one triple bonded, one hydrogen and bromine get attaches to this Br and CH. Br and H, it becomes CH2 CH. Br will be getting bromoethane. Again treat with HBr because double bond now it can reduce to single bond. Again it treat with a bromine. So it will be like this: C carbon hydrogen CH2, and this will be double bond with hydrogen, and here this will be hydrogen. One is bromine, Br. When we treat with again HBr, then we will be getting this bromine. Hydrogen is replaced by this bromine. Will be forming carbon with bromine, and here is bromine and carbon with single bond, hydrogen and hydrogen. What is this? Carbon attaches the same side, and it is called gem dihalide. Gem dihalide. Okay. Next. Not only this, instead of this, you can take propine. Instead of alkyne symmetrical, you can take propine. In the case of propine, then addition to unsymmetrical alkene follows Markovnikov's addition. Negative part of the adding molecule adds to the carbon containing less number of hydrogen. Out of this will be consist one hydrogen. Here consists the three hydrogen. The less number of hydrogen, bromine attaches to this. If bromine attaches to this, it will be formed double bond. Triple bond become double bond. Again treat with HBr, H plus and Br minus. Partial positive charge, partial negative charge. This negative part of the molecule adds to the carbon containing less number of hydrogen again on the same. So we'll be getting 2, 2 dibromopropane. This will addition, unsymmetrical alkene addition follows Markovnikov's addition. Markovnikov's rule or Markovnikov's addition. Okay, you need to remember that. That's too important. Next, next is addition of water. Okay, first hydrogen, next halogen, next hydrogen, halogen, next is water, H2. So, like alkane and alkene, it is also immiscible and do not react with water. However, one molecule of water adds to an alkene on warming with the mercuric sulfate. In presence of Hg plus mercuric sulfate and dilute sulfuric acid at 333 Kelvin to form carbonyl compound. Carbonyl is C double bond O compound. I'll write here. So carbon double bonded compound are called carbonyl compound. Carbonyl compound is nothing but it can form C double bond O. So that is ketone or alcohol. Can able to form ketone or alcohol because those are tautomers. Is nothing but enol form. Ketoenol forms. Ketone means that will be having same double bond. This double bond, if OH group attaches to then double bond reduces to single bond, it forms an alcohol. This also we call as ketoenol tautomers. We'll be studying later the meaning of ketoenol tautomers and other things. Okay, so here addition of water, we'll see the chemical equation. Okay, so this is a chemical equation. First equation. Here in the first equation, ethyne carbon triple bond. So in presence of mercuric oxide, usually it doesn't react with water. Only with the suitable condition, that's mercuric sulfate Hg. So in presence of mercury sulfate, 333 Kelvin degrees Celsius, this OH minus negative part, this OH minus negative part add to the molecule here to the carbon and hydrogen, this side or this side, no problems to us, any one side. And one hydrogen attaches to here, one CH is there and one OH will be get attaches to here. Then what will happen? This will be CH2COH. OH is alcohol. Okay, alcohol. So keto enol, in double bond, in with alcohol, enol. Two ketone. This is keto group, no? Keto group. And this is enol, carbon-carbon double bond, en, and alcohol group, enol. Keto enol tautomers. This is also recorded as an isomers. Will be having same molecular formula, same structural formula. Just the group, substituent group, keto and alcohol group are differ. These are recorded as keto enol tautomers. Here, this OH group, when it is an isomeric form, this hydrogen replaces this hydrogen shift here, then it forms a single bonded compound like CH3. This hydrogen shift here, it becomes CO and this H, O double bonded. So if hydrogen shift one electron or forms a double bond, it forms a ketone. So that is keto enol tautomers, keto enol tautomers. So this is how the addition of water is. And also you can see the propyne, the same chemical reaction with respect to this mercury, using of mercury sulfate, propyne to form propanol, and it is an isomeric form of propanone, ketone, propanone. This is C double bond O ketone, that is not an enol, that is ketone. This is enol, keto, this is keto group, C double bond O, 1, 2. 1, 2 is ketone. 2 no, so ethane, okay, in that ethane, 2, 1, that is ketone, CH3COH, CH3 C double bond O, CH3COH. Okay, next CH3 C double bond OCH3. Okay, H hydrogen, CH3CO CH3, CH3CO CH3. These two are ketones and these two are enols. Keto enol tautomerism will be possible. Okay, with the addition of water molecule. Next is polymerization. We know that polymerization we studied in alkene, carbon-carbon double bonded compound at high temperature. Means carbon-carbon double or triple bonded compounds are treated with high temperature with a suitable catalyst will be forming long chain compound are called and means polymers. Basic unit is carbon-carbon triple bonded compound. Carbon-carbon triple bonded compounds. So you need to see this equation here, triple bonded compound. In this triple bonded compound, linear polymerization will takes place. One bond will be shifted here, one electron. So what it will be forming? CH, hydrogen will add to this. One will be shifting here. So it will be forming C double bonded, one electron shift, no, say double bonded. To that another will be shifting to this, will be forming double bonded. And the N number, it will be forming the long chain compound is called polyacetylene. Ethyne to a long chain compound, N number of compound will be forming is called polyacetylene compound. Polyacetylene. Thin film of polyacetylene, it is used as electrodes in batteries. And the films are good conductors, the lighter and the cheaper than the metal conductors. Compared to metal conductors, polythene sheet is the transparent sheet. It is polymerization of polyacetylene. What we are getting, it's a transparent sheet, which will be having high molecular weight. The polythene will be consisting the repeating unit of CH double bond CH, CH single bond double bond CH2. This is the repeating unit. Okay. Polyethylene, long chain of polyethylene is called an polyacetylene. So which shows an polymeric nature because of double and triple bonded compound. Okay, polyethylene we studied in earlier polyethylene. So now polyacetylene, carbon-carbon triple bonded compound. Okay, and we'll see last reaction, that is cyclic polymerization. This is straight linear polymerization. Cyclic polymerization, first carbon links to last carbon can able to get like benzene. Benzene we can able to prepare. Ethane and passing through the red hot iron tube. This is important. You need to remember this equation. Ethane and passing through the red hot iron tube at 873 Kelvin undergoes cyclic polymerization. Three molecules of polymerizes to form benzene. You can notice here triple bond. This is in a triple bond. This is a triple bond, and this is triple bond, triple molecule. So at red hot iron, heating the red hot iron tube at 873 Kelvin, then what will undergoes here? One bond will be shifting, electron shift here, one electron shift here, forms a bond, and one electron shift here, one electron shift here, forms a bond, one electron shift here, and one more electron shift here, forms a bond. Is nothing but carbon, 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 here carbon, and here carbon, and here carbon. Now total, this is one pair, this is one pair, this is one pair. Out of this, so I'll change the color. This is one pair. Out of this, triple bond, double bond, one bond shift here, single bond. Then here is a double bond. And what I marked in a green ink, blue ink, that is the ethyne. In that one electron will donate, no, form cyclic ring, is like benzene. Is like benzene. We can able to prepare benzene from the ethyne. This is cyclic polymerization. Cyclic polymerization. So will be continue from here. Cyclic polymerization, aromatic hydrocarbon will continue in the next session with aromatic hydrocarbon. So in this session, what we studied from the alkynes, how is the triple bond, what is the type of bonding, what is the general formula. Okay, homologous series we studied in the beginning. Next, structure. After that, we studied structure of alkyne, that is linear 120, and two unhybridized orbital will be present, that is planar. It's 180 means linear, it will be. Next, after that, we studied nomenclature, naming in that isomer. We studied already nomenclature. Next, isomerism. Next, preparation, the two important method of preparation. One is from calcium carbide, CaC2. Next is vicinal. Next is from vicinal halide or geminal halide, gem dihalide. Next, after that, physical properties. What we studied? After that, physical properties. Next, after that physical property, next is chemical properties. In chemical properties, first one is acidic nature. Acidic nature, that's alkynes are treated with soda amide, sodium metal or soda amide. So we'll be forming alkanide. So monosubstituted, disubstituted, alkanide or ethanide compounds. Next, the addition reaction. Next, after that, addition reaction. In addition reaction, addition of dihydrogen using platinum palladium catalyst. Next, addition of halogen using CCl4 carbon tetrachloride. Next, addition of hydrogen and halide HX. Next, addition of H2O. It is difficult. At higher temperature, we are using mercury. We'll be using the mercuric sulfate or mercury Hg at 333 Kelvin. We can able to get the alcohol, ketone and alcohol, that addition of water. Next is polymerization, cyclic polymerization and linear polymerization. That's about the alkynes, carbon-carbon triple bonded compound. In next session, we'll study about aromatic hydrocarbons.